Okay, we're moving on to chapter 2, and we're going to start looking at derivative and the tangent line. Um, when we're talking about finding a tangent line, finding the slope of a tangent line at any given point, we're given this equation right here. And I can explain to you quickly how that equation is formed. If we're talking about some curved line, and that's what we're going to start finding, we're going to start finding the slope of a function at curved lines. And what we're going to use, we're going to use a tangent at that line, or at that point on this curved line. So we're going to use a tangent line. A tangent line is just a line that touches a line at just one little point right there. That would be the tangent line. Just barely touches that graph at that point right there. All right, so that's a tangent line. In order to solve for the slope of that tangent line, all right, we're going to take the limit of a secant line. So we're going to pick a point out here. So say I have some x value c here. All right, I'm going to pick a point to my right, and I'm going to pick a point. We're going to call it change of x. I'm just going to move over change of x some distance to the right. All right, and what we're going to do is we're going to take the limit as this point gets closer and closer and closer to our original point c, and that's going to end up eventually until our point that we're changing to the right is going to fall right on top of it. And that's where we have just a tangent line. So we're going to start with a secant line. And where this formula comes from is it's actually we're finding the slope of the secant line. We know how to find the slope of a straight line. All right, so our x value for our original point right here would be c. And to find the y value, we just plug it into our function. So f of c, that would be our point here. For our second point, well, it would be our c plus our change of x. Whatever we decided to move it to the right would be our x value. Sorry, that parentheses shouldn't be there. It should be a comma. And our y value would be f times c plus change of x. So if we were looking to find the slope of that secant line, we'd go y2 minus y1. So we'd have f of c plus change of x minus f of c. All over the change x2 minus x1. So x2 is c plus change of x, and we're going to subtract our x1, which is c. Well, you notice that this plus c minus c, this is going to drop out, and there we have our formula right there. And what we're doing then is we're looking as this point gets closer, so we're taking the limit as our change of x, so our distance we're moving to the right, becomes closer and closer to 0 to where it is, so we're taking the limit as that approaches 0. So that's how we're going to find the slope of tangent lines. All right. So our first example, we're going to use this equation up here to find the slope, all right, of the graph 2x minus 3 at the point 2, 1. Well, we should know from what we know in y equals mx plus b that slope should be 2. But we're going to show you how this formula works to find the slope at just any given point, and we're going to start with something that we should know. So we're going to take the limit as change of x approaches 0. Of f of c was our x point, so f of 2 plus change of x minus f of c, which is our x point again, f of 2, all over change of x. Well, anytime you see f of what's inside the parentheses, you go ahead and you plug that in for x. So we're going to take the limit as change of x approaches 0 of 2 times 2 plus change of x minus 3, because that's the function. That's it right here. Just plugging 2 plus change of x in for x. And then we're going to subtract 2 times 2 minus 3. We're just plugging 2 in to the function to the left. All right, all over change of x. Okay, so we're going to distribute. So we're going to have 4 plus 2 change of x minus 3 minus, well, this is going to be 4 minus 3, which is going to be minus 1, right? All over change of x. And again, we're still taking the limit as change of x approaches 0. Combine like terms. So if I combined our just constant terms here, 4, negative 3, and a negative 1, this would make negative 4. So those actually end up canceling out. What we have left over is the limit as change of x approaches 0 of 2 change of x over change of x. Well, since we're multiplying, these two can cancel out. So now we have the limit as change of x approaches 0 of 2. Well, we know since there's no change of x in this equation, it's the limit of a constant, we know that that limit's going to be the 2. So the slope, like we said it should be, of 2x minus 3 at the point 2, 1 is 2. All right, so here we're going to do it slightly a little different. Well, now we have a curved function. All right, so an x squared plus 1. We know that's a parabola. So we want to find the slope of this graph actually at 2 points. So what we're going to do is we're going to find the slope of the tangent line for any point on the line. So we're going to do in general, instead of picking a point of x for our c, we're just going to let x represent our c. So we're going with the point x, f of x. All right. So instead of plugging 2 in like we did in the last equation, we're going to plug in x. So we want to find the limit as change of x approaches 0 of f of x plus change of x minus f of x, because we're using x instead of c in this case, because we want to figure a general equation so we can just find one equation so we can plug the x values in for both these points and find our slope. All right, so I'm going to go ahead and plug in x plus change of x into our equation. So the limit as change of x approaches 0, plug x plus change of x, so I'm going to have x plus change of x squared plus 1 minus x squared plus 1, because that would be my f of x, all over change of x. All right, when we square this isn't just x squared plus change of x squared. Obviously, we have to FOIL that. So we're going to have square the first term, x squared, multiply the 2 and double it. So 2 change of x, x times the change of x, and then plus change of x squared plus 1 minus x squared, and I'm just going to distribute my negative sign, minus 1, all over change of x. We're looking at the limit as change of x approaches 0. Combine like terms, and I'm going to see that there's a positive x squared and a negative x squared. Those will cancel out. I'm also going to see that there's a positive 1 and a negative 1. Those are going to cancel out. So what I'm left over is 2 times the change of x times x plus the change of x squared all over a change of x. And we're still taking the limit because change of x approaches 0. All right, so what I would do up top, I guess, or you can just look at it, we notice that there's a change of x in each term, so we can go ahead and we can take a change of x and cancel 1 out. So what I'm left over on the top, or what I'm left over with, is the limit as change of x approaches 0 of just 2x plus change of x. Well, we're taking the limit as x approaches 0. We know as long as it's continuous, we can go ahead and we plug 0 in. And so now when we take the limit, we know our limit is just 2x. So to find the slope of the slope of the tangent lines of these 2 points, we just go ahead and plug our x value in. So the slope for any point on that function is going to be 2x. We just plug the x value in. So for 0, 1, it's going to be 0. And at negative 1, it's going to be the slope of negative 2. Okay. A vertical tangent line, if we were to go through that stuff and our limit would be negative infinity or infinity, we'd have a vertical tangent line, which is say we don't have a slope, right? So the derivative of a function is actually the definition of derivative of f is what we just did up above. And that's all it is. When we're talking about derivatives, we're finding the slope of tangent line. And so that's what we did. Other names for derivative, f prime of x, dy dx, y prime, d dx of f of x, or dxy. Just different notations that you'll see in the book. We're going to use the definition of derivative to find f of x in this function right here. So we know that it's f of x plus change of x minus f of x all over change of x, and the limit as change of x approaches infinity. So I'm going to take the limit, change of x approaches 0, of f of change of x plus x minus, or x plus change of x, doesn't matter, minus f of x all over change of x. So I'm going to plug change of x plus x in. So I have 2 times change of x plus x squared plus change of x plus x minus 1 minus 2x squared plus x minus 1. It's minus that whole quantity. That's why I put that parentheses sign there, because we're going to make sure we distribute our negative sign. So we're going to go ahead and square this out, and I'm going to have 2 times change of x squared plus 2x change of x plus x squared. Nothing changes over here, plus change of x plus x minus 1. I'm going to distribute my negative sign. Sorry, that should be, yeah. Minus 1 minus 2x squared minus x plus 1. Alright, so we're still all over the change of x, and we're still taking the limit as change of x approaches 0. Go ahead and distribute. I'm going to have 2 change of x squared plus 4x change of x plus x squared. Oh, I didn't really need that parentheses. Let's get rid of that. And then we're going to have plus change of x plus. Oh, I messed up there. I'm getting a little messy here. All right. I didn't leave myself enough room, so I'm going to have 2 change of x squared plus 4x change of x plus 2x squared plus change of x. I missed my 2x squared earlier. Plus x minus 1 minus 2x squared minus x plus 1. Still all over the change of x. I know this looks messy. The great thing about derivatives is a lot of stuff's going to cancel out. If you notice, there's a 2x squared and a negative 2x squared. That's gone. We have an x and a negative x. That's gone. We have a negative 1 and a 1. That's gone. All right. So all we have left over is 2 change of x squared plus 4x change of x plus a change of x. Still all over change of x. If you notice, each term has a change of x in common. So we can get rid of at least one change of x out of all these. So that becomes a 1. This becomes just out of there, and this guy becomes a 1. So what we have left over is 2 times the change of x plus 4x plus 1. All right. And we're still taking the limit as change of x approaches 0. So I plug 0 in, this becomes 0, and all I have left over is 4x plus 1. So my derivative of that function is 4x plus 1. The last little part here, if f is differentiable, so we can take the derivative at x equals c, then it's obviously going to be continuous at x equals c. One thing to note, though, however, is the converse is not true. If f is continuous at x equals c, then f is differentiable at c. That is not true. You can look at your examples on page 6, or examples 6 and 7 on page 97. And I'll come back and we'll do this example in the next video because I'm running out of limit for YouTube video. So we'll see you in the next video.